Hello everyone, welcome back to our operating system lecture series. I am Mrs. Namita Amrutkar and today we are going to begin a new and very important topic, memory management. Memory management is the process of managing the computer's main memory efficiently. It is one of the core functions of an operating system because every program needs memory to execute. The operating system is responsible for allocating memory to a process, keeping track of memory uses, protecting memory from unauthorized access, and freeing memory when it is no longer needed. In this lecture, we will understand the basic concept of memory management, why it is important, how the operating system ensure efficient utilization of memory. So, let's start with memory management. Now, let's understand the concept of logical address space and physical address space, which are fundamental to a memory management. A logical address space is virtual address generated by the CPU while a program is running. Every time a program needs to access memory, the CPU create a logical addresses. These addresses are not the actual memory location. Instead, they are virtual address used by the program. The collection of logical address generated by the process is called as a logical address space. The logical address space act as a reference to access memory, making it easier for program to execute without worrying about the actual location of data in a RAM. Now look at the uh, physical address space. The physical address space represents the actual location in the computer memory or a RAM. These are the real memory address where data and instruction are stored. Unlike logical address, physical address are not visible to the user or the running program. The conversion from logical address to physical address is performed by special hardware component called a memory management unit, or we can also in short form we call it as a MMU. Whenever CPU generate logical address, the MMU automatically translate it into the corresponding physical address before the memory is accessed. Now let's understand the next concept of memory management, dynamic loading. Dynamic loading is a memory management technique in which a program or its module are loaded into a memory only when they are needed it during the execution. Instead of loading the entire program at the beginning, only the required parts of the memory will be loaded. This helps in using memory more efficiently. One of the main feature of dynamic loading is that program is loaded only when it is required. If a particular function or module is never used, it is never loaded into the memory. As a result, unnecessary memory usage is avoided. Another important feature of the dynamic loading is that it reduces memory usage and improve system performance. Since only the required module occupy memory, more memory become available for another program, allowing the system to execute multiple processes efficiently. In dynamic loading, the entire program is not loaded into a memory before execution. Instead of different modules are loaded dynamically whenever they are called by the program. This makes the execution more flexible. Dynamic loading also provide greater efficiency and flexibility because the operating system load only the component that are actually needed by the user. The result is faster startup time as the system does not waste their time for loading unnecessary module. Another feature is that all the required modular libraries are already built and stored, but they are loaded into a memory only when the program requests them for execution. Overall, dynamic loading is effective techniques for improving memory utilization, reducing unnecessary uh, occupying memory, increasing flexibility, and speeding up program execution by loading only required parts of the program when they are needed. Now, let's understand dynamic linking with the help of this diagram. The process begins with the source program, which is the program written by the programmer. This source code is sent to the translator such as compiler or interpreter, which convert into a machine code, and that code is called as a object module. The object module contains machine code, but it is not yet ready for execution because it may still need external libraries. Next, the linker takes the object module and combine it with the required libraries in dynamic linking. Instead of permanently including all library inside the executable, the linker only create a reference to the required shared library. This keeps the executable file smaller. The linker then produces a uh, library files, which is passed to the loader. The loader is responsible for loading the binary program into the main memory for execution. An important feature of dynamic linking is that shared libraries are loaded only when they are actually needed during program execution. If the program never call a particular library function, that library is never loaded into a memory. This approach has several advantages. Since common libraries are shared among multiple programs, memory usage is reduced. The executable file size also becomes smaller because it does not copy all library files. In addition, if a shared library is updated, all program using that library can benefit from the updated without using the uh, recompile it. However, dynamic loading also has a limitation. Since the required library are loaded at runtime, the program depends on this library being available on the system. If we required a library is missing or incompatible, the program failed to execute correctly. Now we will understand the different memory allocation techniques. Memory allocation is the process of assigning a memory space to a process so that it can execute properly. It is important part of memory management because it helps the operating system use available memory efficiently. There are two main type of memory allocation technique. First one is contiguous memory allocation technique and the second one is non-contiguous memory allocation technique. In continuous memory allocation, each process is stored in a single continuous block of memory. The entire process is loaded into one section of the main memory. This technique is simple and provide faster access, but it may cause fragmentation problem because memory block can become unused after that particular process is removed. Continuous memory or allocation is divided in two types. First one is fixed size partition schema and the second one is variable size partition schema. In this method, in the fixed size partition method, the main memory is divided into a fixed size partition before the execution of the process. Each partition can store only one process at a time. If the process is smaller than the partition size, the remaining memory space is wasted. This unused space inside the partition is called as an internal fragmentation. For example, if a partition size is 10 MB and the process required only 6 MB, the 4 MB of memory remain unused. The advantage of fixed partition is that it is simple and easy to implement, but it may lead to a memory wastage. The second subpart of the continuous memory allocation is variable size partition schema. In this method, a memory partition created dynamically according to the size of process. The operating system allocate only the required amount of memory to each process, which is reduce the internal fragmentation. However, when processes are loaded and removed frequently, small unused space are appear between the allocated memory block. This problem is called as a external fragmentation. For example, if a process require 15 MB operating system and create 15 MB partition instead of assigning a fixed size block. The next one is a non-continuous memory allocation. In a non-continuous allocation, the process is divided into a smaller part and stored at different location in memory. Uh, In this technique, paging and segmentation are some example of non-continuous memory allocation. Therefore, memory allocation techniques helps the operating system manage memory efficiently and improve the performance of multiple processes. Now, let's understand the new concept paging. Sometimes program may need more memory than the RAM physically installed into the computer. To solve this problem, the operating system use virtual memory. Virtual memory is a part of the hard disk or SSD that act like a extra RAM whenever the actual RAM becomes full. Although slower than a RAM, it allows the system to run larger programs and multiple applications at the same time without running out of memory. To efficiently manage virtual memory, the operating system uses a technique called as a paging. In paging, the memory required by a process is divided into a small fixed block called as a pages. The size of each pages is always a power of 2 and typically ranging from 512 byte to 8192 bytes. The size of a process is measured by the number of pages it contains. Similarly, in computer's physical memory, RAM is also divided into a fixed size block called as a frame. An important point is that the size of the frame is exactly same as the size of page. This allows any page to fit perfectly into available frame in memory. When a program runs, its pages are loaded into available frame instead of requiring one continuous block of memory. This improve memory utilization and completely eliminate external fragmentation, which occur when the free memory is scattered into a small blocks. To efficiently manage virtual memory, the operating system uses a technique which is called as a paging. In simple word, we can say that virtual memory allows the computer to use hard disk space to extra memory, while paging divides both the program and the physical memory into equal size block and making memory management more efficient and allowing large program to run smoothly. Page fault occur when a running program tries to access a page that is a part of virtual memory but is not loaded into a physical RAM. Since physical RAM is much smaller than virtual memory, page fault are normal part of memory management. When a page fault happens, the operating system first check if the required page is on the secondary storage, such as on the hard disk or SSD. If there are free space in the RAM, the page loaded directly. However, if RAM full, the operating system replace an existing page with the required one. To decide which page should be removed, the operating system uses page replacement algorithm, which is first in first out, optimal page replacement, least recently used and most recently used algorithm. Each algorithm follow different strategy, but they all have the same objective to minimize the number of page fault and improve system performance. In short, a page replace algorithm help operating system to manage memory efficiently by choosing the best page to replace whenever a page fault occur. Now, let's understand first in, first out or a FIFO page replacement algorithm. FIFO is among the algorithms very simplest algorithm. It works in the principle first come, first out. This means that the page that has been in memory for the longest time is the first to be removed when a new page needed to be loaded. The operating system maintains all the pages in a queue. The oldest page is placed in front of the queue while the newest page is added to the rear. Whenever a page fault occurs, there is no free space in memory. The page at the front of the queue is removed and the new page is inserted at the end. The main advantage of FIFO is that simple to understand and easy to implement. However, it has a major disadvantage. It does not consider how frequently or recently a page has been used. As a result, we have to remove a important page that will be needed again very soon, causing more page fault. Our interesting problem associated with FIFO is called Bell-Eddy anomalies. The phenomenon shows that increasing the number of page frame can sometimes also increase the number of page fault, which is the opposite of what we normally expect. For example, if the reference range is suppose 3210, 32104, okay, and we have three slot, that means a three-page frame. The total number of page fault is 9. Surprisingly, when the number of page frame is increased to 4, the total page fault becomes 10 instead of a decreasing. This unusual behavior is known as a Bell-Eddy anomaly. So while FIFO is simple and easy to implement, but its poor replacement decision and the possibility of Bell-Eddy anomaly make it less efficient than more advanced algorithm like RLRU or a optimal. Now, let's understand the FIFO or first in first out page replacement algorithm with the help of these examples. FIFO is the simplest page replace algorithm. It follows the principle first in first out. This means that the page that enters memory first is called also first page of the where to remove it whenever a page replacement is required. The operating system maintains the pages in a queue. When a page fault occurs and all page frames are occupied, the oldest page at the front of the queue is removed and this new page is inserted at the end. Let's look at this first example. The page reference string are given 1, 3, 0, 3, 5, 6 and 3. Initially, all pages frames are empty and we have also given the page frame is 3. Page 1 is inserted into the memory, so it is loaded. This is the page fault. Next, page 3 is also not present, so it is loaded, another page fault. Then 0 is loaded, again a page fault. The next page is 3. Since it is already present in the memory, it is a page hit. So no page replacement is needed. Next come 5. uh, uh, 5 memory is a full and people removes the oldest page. The oldest page is 1 and load 5. This is page fault. Then page 6 arrives. The oldest page is now 3, so it is replaced by 6. Okay. Another page fault. Finally, page 3 is a reference string, which is already again it is no longer main memory. Again, we because it is removed, so FIFO replace the oldest remaining page. The oldest remaining page is 0 with 3. This is called as a page fault. So in this example, we have 6 page fault and 1 page hit. Now let's move to the second page replacement algorithm. Now let's understand optimal page replace algorithm. In this slide, I have shown two example of optimal page replace algorithm. First one I will explain, and the second one you have to solve it your own. The optimal page replacement algorithm is considered a most efficient page replace algorithm because it always replaces the page that will not used for longest time in the future. Okay, since it uses future knowledge, it produces a minimum possibly number of page fault. However, in real operating system, it cannot be implemented because the future page reference are not known in advance. Therefore, it is mainly used in as a benchmark to compare other page replacement algorithm. Let's understand this with the page referencing are shown over here 7, 0, 1, 2, 0, 3, 0, 4, 2, 3, 0, 3, 2 and 3. And the number of page frame are given is 4. So I had draw here the four boxes over here. Initially all frames are empty. So the first four page 7, 0, 1, 2 are loaded into the memory, and these all are page fault. We have inserted 7, then 0, then 1, then 2. Okay, all these are the page fault. The next reference is 0, which is already present in the memory, so it is a page hit. When page 3 is arrived, okay, then memory is full, the algorithm look ahead in the reference string and replace the page that will use the farthest in the future, which is page 7. This gives a page fault, but it is the best possible replacement. The algorithm continue in the same way, always checking future reference before replacing a page. Whenever the required page is already in the memory, it results in a page hit. At the end of this example, the total number of page fault will be occur 8. Okay, and this one is the second example. You have to try to solve it your own. I have already solved it, and you have to check your answer which give correct or not. Now let's discuss two important page replace algorithm: least recently used and most recently used algorithm. First, let's understand least recently used. LRU replace the page that has been used for longest period of time. This idea is that if a page has not been used recently, it is less likely to be needed again soon. This makes LRU more efficient than FIFO in many situations. I have shown this in the example. Here the page reference string are given 7, 0, 1, 2, 0, 3, 0, 4, 2, 3, 0, 3, 2, 3 with page 4 page frame. Initially, the first 4 pages are loaded, causing page fault. After that, whenever a page replacement is needed, LRU remove the page that we used longest time ago. By following this rule throughout the reference string, the total number of page fault occur is 6. Now let's move to the most recently used. MRU follow the opposite approach. It replace the page that used most recently, assuming that most recently accessed page may not be needed again immediately. Although this strategy works well in a special cases, it is generally less efficient than LRU. Using the same page reference and 4 page frame, MRU replace the most recently page whenever page fault occur. So in this example, the result is total 12 page fault, which is much higher than LRU. So to conclude, we can say that LRU is the most widely used page replace algorithm because it keeps frequently used page in memory and usually give fewer page fault. On the other hand, MRU replaces the most recently used page and generally produce more page fault, making it less suitable for most applications. Now, we had to learn a new concept, segmentation, which is another memory management technique used in operating system. In segmentation, a process is divided into a segment instead of a fixed pages. These segments are not necessary of the same size. Each segment represents a logical part of the program, such as main program, function, data, stack, or heap. Unlike paging, segmentation provide user logical view of the program. Each segment is mapped separately into physical memory, making memory management more flexible. There are two types of segmentation. The first is virtual memory segmentation. In this method, a process is divided into a multiple segment, but all segments are not loaded into a memory at the same time. Segments are loaded only when they are required during execution. This helps in efficient memory utilization. The second type is the simple segmentation. In this method, a process is also divided into a multiple segment, but all segments are loaded into memory when the program start. These segments do not need to store next to each other in physical memory, so they can be placed in different memory location. Now let's understand the logical address generated by the CPU. Logical address segmentation has a two part. First one is segment number and the second one is segment offset. The first part represented by yes, it defines which segment of the program is being accessed, and the second part is segment offset, which is represented by B. It specifies the exact location of a displacement within the particular segment. So the CPU uses the segment number to locate the correct segment and the offset to access the data inside that segment. In conclusion, we can say that segmentation divide a program into a logical variable size segment, making memory management more flexible and matching the program's view of the program. It is especially useful for organizing large program into a meaningful parts such as code, data, and stack. Now let's understand the concept of deadlock in operating system. A deadlock is a situation where two or more processes are blocked because each process is holding a resource and waiting for another resource that is held by another process. As a result, none of the process can continue their execution and the system come to a standstill. Simple real-time example, two trains coming toward each other on the same track. Since there is only one track, both trains stop and wait for another to move, but neither train can move first, so both remain blocked. This situation is similar to a deadlock in an operating system. Now let's understand the diagram shown in the slide. There are two processes, process 1 and process 2, and two resources R1 and R2. Initially, resource R1 is assigned to process 1 and resource 2 is assigned to the process 2. After some time, process need a resource 2 to continue its execution, but resource 2 is already occupied by process 2, so process 1 start waiting. At the same time, process 2 need a resource 1, but resources 1 is already occupied by the process 1, therefore process 2 also start waiting. Now both processes are waiting for each other to release their resource, since neither process can proceed to or release the resource. Both remain blocked forever. This situation is called as a deadlock. That means a deadlock occur when processes are waiting infinite time for resource held by one another. It causes the affected resource to stop executing, making efficient deadlock prevention, avoidance, or recovery an important part of an operating system design. Characteristics of a deadlock. The first characteristic is mutual exclusion. This means that a resource can be used by only one process at a time. If one process is using the resource, no other process can access it until it releases. For example, if process P1 is holding a resource R1, then no other process can use resource 1 at that moment. The second characteristic is hold and wait. In this condition, a process holds one or more resource while waiting for additional resource that are currently held by another process. For example, process 2 may already have a resource 2 and a resource 3, but it is waiting for resource 1, which is currently being used by the process 1. The third characteristic is no prevention. This means that a resource cannot be taken away forcefully from a process. A resource can be only be released by the process after it completed tasks. For example, process 2 cannot force process 1 to release the resource 1. It must be wait until the process 1 finish out its execution and release the resource. The fourth characteristic is uh, we can circular wait. This happens when a group of process form a circular chain where each process is waiting for a resource held by the next process in the chain. For example, process P1 is waiting for resource R1 and which is held by process P2, while the process P2 is waiting for resource R2 which is held by the process P1. Since both are waiting for each other, neither can proceed for creating a deadlock. To conclude, a deadlock occurs only when all these four conditions mutual exclusion, hold and wait, no prevention, circular wait exist at the same time. If even one of these conditions is prevented, the deadlock can be avoided. Now let's discuss the method of handling deadlock in an operating system. There are three main methods used to deal with deadlock. These are deadlock prevention, deadlock avoidance, and deadlock detection and recovery. The first method is deadlock prevention. In this approach, the operating system prevents deadlock from occurring by ensuring that at least one of the four necessary conditions for deadlock is never allowed to happen. For example, it may be force process to request all required resource at once or allow resource to be shared whenever possible. Since one of the necessary condition is removed and deadlock cannot be occur. The second one is deadlock avoidance. In this method, the operating system carefully check every resource request before granting it. A resource allocated only if the system remain in a safe state. After the allocation, if he granting the request could be lead be a deadlock, the request is denied. A well-known algorithm used for deadlock avoidance is the banker's algorithm. The third method is deadlock detection and recovery. In this approach, the operating system does not prevent or avoid deadlock. Instead, it allows deadlock to be occur. Continuously check whether deadlock has happened and then takes an action to recover from it. Recovery may involve terminating one or more resource or taking away resource from the certain process so that deadlock is broken. To conclude, we can say that a deadlock can be handled by a three-way: prevention, stop them from the occur; avoidance, allocate resource carefully to keep the system safe; and the detection and recovery identifies deadlock after they occur and then we have to remove it. Thank you everyone for your attention. In today's presentation, we learn memory management techniques, page replacement algorithm such as FIFO, optimal, LRU, MRU. We also discuss segmentation and finally we learn overview of deadlock and its four necessary condition and different method used to handle a deadlock. I hope this presentation has helped you to understand this important concept. Thank you for listening.